Hello, good morning. Dengar tak ni?
Dengar, Doktor.
Dengar Okay. Sekarang dah ni, masuk 44. Lagi berapa? 8 orang lagi. Okay, Assalamualaikum, good morning.
Good morning, Doctor.
So, yeah. Okay, today we will continue our lesson to chapter 8. Okay. We still have two chapters, chapter 8 and chapter 10. And then our last date for this SEM is 27. Okay, 27 January. So this week for chapter 8, maybe this week and plus Sunday next week. And then from Sunday next week, after 27, maybe we'll continue to chapter 10. Okay. Okay, let's continue order dulu. Macam nak matikan ni. Chapter 8 is about steady-state non-isothermal reactor design. Okay. Until now, from chapter 1 to chapter 6, you have studied about the isothermal reaction only. Okay. Then from chapter 8 and chapter 10, you can non-isothermal. Okay. So there is a change in temperature. Okay, so you have to consider the temperature, initial temperature and reaction temperature. Okay, so after chapter 8, you will able to describe the algorithm for CSTR, PFR and PBRs that are not operated isothermally. Okay, and then you can also, as usual, size adiabatic and actually non-adiabatic we will not study. Okay, adiabatic, CSTR, PFR and PBRs. Okay, for the final exam, actually, one of the lecturer have a question about the non-adiabatic, but because we usually we do not touch about the non-adiabatic, so he changed the question to adiabatic only. Okay, and then you can also able to use reactor staging to obtain high conversion for highly exothermic reversible reaction. Okay, let's start. Okay, energy balance. Have you studied about the energy balance before? Hello.
Yes, Doctor.
Yes, Doctor.
Okay, so I think you already know about energy balance. So, okay, here also we use the energy balance. Okay, let's calculate the volume as usual. The volume necessary to achieve a conversion X. Okay, this is an example. In a PFR, for a first order exothermic reaction carried out adiabatically. Okay, so for adiabatic exothermic reaction, the temperature profile might looking something like this. Okay, at the beginning, like this, and then increase, and then flat. Okay, by the increasing V, and then the temperature increase. Okay, so because PFR, so the same because of the PFR, so the mole balance equation always same so the V equal FA naught integration for this one. Why this one? Because this is first order. You can imagine this is A to B. So the first order, so negative RA equal ACA. So CA equal CA naught in bracket 1 minus X, because V equal FA naught integration dx over negative RA. Okay, and then we have because we have to think or consider about the temperature. There is no other equation for the temperature, just this one. Okay, this is what we call what equation? Arrhenius equation. Okay, so now we have two temperature. We call the temperature change. Okay, so we have T1, T initial, and T2. Okay, after duration or during duration. Okay, and then because we have two temperature, so we will have 2K. Okay, this is K1 and K2. You see, if you forget, you remember this K2 equal function of T equal K1 exponent. This is 2, this is 1, so this is 1, this is 2. Exponent E energy, activation energy, R gas constant, in bracket 1 over T1 minus 1 over T2. This is to get the K2. Okay, so the combined mole balance, this one, red law, this one, and stoichiometry yield next. Okay, tu hilang lah kat sini. I think this one, no. Need to relate. When we want to relate X and T, use the energy balance. So become like this. We want to relate X and T. So this is X, this is T. So if we want to relate that one, this is the summary. Okay, the usual friendly forms of the energy balance will focus on are outlined in the following table. Actually, this is in your, you can get also it from your textbook. Okay, there is a summary for all of the X, the relationship between the X and the T. Okay, you can get what we will study. Just number one, this one. Number two, we will not study, okay? Because here we have the heat exchanger. We have to consider about the heat exchanger, UAT. So this will not cover in chapter 8. So just this one, okay? So if the important one in chapter 8 is you want to relate the X, the combustion, and the T, okay? So this is one, when you want to get the X energy balance, you have to get the X energy balance equal, you just remember this is the equation. Okay, you can know if you want how to get this equation. There is a the sequence. Okay, the later you can study how to get this one. Okay, how they derive to get this one. Okay, here you just remember X EB, X for energy balance is equal sum of sum for theta I times CPI, heat capacity, CPI head, and then bracket T minus T naught over negative delta H ration, delta heat operation. Okay, and then from here, if the ration may be just A to B, and this become like this. Okay, can you accept? Can you understand? Okay, if just A, so become like this. Okay, CP T minus T naught over minus A X RX. Okay, so if you want to get the T, you have to bring the T here. Okay, so you can get like this. Rearrange T, you can get like this. Okay, this is from here. Okay, so the chapter 8, you can they may the lecture the exam in the exam maybe they want you to calculate for the x or for the t or both. Okay, so you have to remember this equation. Okay, you can see in that equation in the textbook also. And then there is some example in the textbook. You can see how they calculate this one. Okay, please see, read the book. Okay, this is we will not cover this one. Okay, this is we have many equation. Okay, this is PFR PVR with heat exchange. Okay, in term of x, for this one in term of x, so you will not study about this, but I just say that for the PFR PVR, maybe you will use in your design next sem. There is the heat exchanger, all that one PFR PVR you can see here. Okay, it's also use heat exchanger. Then also for multiple reaction. Okay, you can see in term of flow rate. Okay, in term of x, you can see the x, this is flow rate, no x. Okay, apa, similar with the previous one, the apa you calculate in term of x or in term of other than x, which is in term of flow rate. Okay, so these equation are derived in the text. These are the equation that we use to solve relation engineering problems with heat effects. Okay. Okay, this is if you want to study about this one, I think about all from where they get this one, you can start with this GMBE. Okay, energy balance. In the material that follows, we will derive the above equation. Okay, you can study from here. Okay, for example, energy balance, the rate of accumulation of energy within the system, DE system over DT equal rate of flow of heat to the system from the surrounding minus rate of work done by the system on the surroundings, and then plus rate of energy added to the system by mass flow into the system, and then minus rate of energy leaving the system by mass flow out of the system. So from here you can derive typical units for each term are joule. Okay, joule over second, or this is watts. Okay, this is the flow diagram sketch for the system. Okay, you can see flow in. What is H? Heat yang masuk. And then this is work. This is flow rate out, flow out H out. Okay, so that equation become like this. This is the Q. You see you see Q, W, FE, FE in, FE out. So you can see Q minus W plus FE in minus FE out equal the system over dt. Okay, this is the step. Okay, folks, here is what we are going to do to put this above equation into a usable form. Okay, how to derive from this. They said how they derive from this one. You see that one, Q minus S, that equation, to become the simple one, that you see in the first equation. Okay, so they have to replace the EI by EI equal this one, HI minus PVI, and then express this one in terms of enthalpies for formation and heat capacities, and then express Fi in terms of other than conversion or rates of reaction, this one. Okay, and then this is for E1, E energy. And this one, you express this one with other this one, and then the F this one, and then define the delta HRX. Okay, and then define the delta CP, and then lastly you manipulate so that the overall energy balance in either in terms of user friendly equation. You can see in this one, 1A 1B, this is in textbook, 1A 1B 3A 3B or 4, depending on the application. What they mean is this one. Okay, this is the yellow box. You can see this one, 1A 1B, 2 3A 3B, and then etc. Okay, you can get that one. Okay, by change all this one in and put here. Lastly, you can get the simple one. Okay, this is the step if you want to study for the step. Okay, this is the step. Sometimes you have to ignore some equation. Okay, and then this is for the Fi, flow rate. You use this one. Okay, then use the theta. Theta, what is theta? Theta is this one. Okay. Okay, lastly you use this one, and then you can get what you want. Okay, this one from the first equation, from the first lah. Lastly, you can get, this is the last the equation that you use in the box, the blue box, not the yellow, for this slide. Okay, for constant heat capacities, you will use this one. Okay, in which the beta equal, there's beta gamma equal 0, and you can equal 0, and then alpha equal CPI. So you just remember this equation to get the X. Okay, this is the example, one of the example of the problems there for the chapter 8. Okay, this is the simple one. You have to do this one before you answer for the next question in the exam. Okay, these are the basic one. So because you have this one, okay, you want to calculate X or T, you have to calculate this one first, and then you have to know this one. Okay, then you this okay, you see, calculate the delta HRX. Okay, they want you to calculate delta HRX, delta CP, and delta HRX. You see, this is delta Rx not. Okay, this is delta Rx at temperature 400. Okay, this is what temperature for the not in energy balance? Zero temperature or what? Hello? Hello? Ada orang tak ada ni?
Ada.
Ada. What temperature? Zero temperature or what temperature?
At the standard temperature.
Standard temperature is what temperature?
Room temperature like 25 degree.
Okay. 25 degree, okay? 25. Tu siapa tu Go
Ya, doktor.
Go seorang je dalam kelas, Okay. So this is the heat operation at standard temperature, which is at 25 degrees Celsius. Ini yang at 400. Okay. Okay. This question want you to calculate for this one. For the reaction A minus 2B plus C. There are inerts, inert for is I symbol for inert present in the system. So they give you the additional information like this. Okay, 298 is 25 kan? 25 degree kan? 273 campur 2, 25. Okay, and then they give you all the heat for each species standard heat. And then they also give you this one, mean heat capacities for all species. Okay. So how to calculate this one? You will use lastly you will use this one. No lah. They just want you to calculate this one. Okay. So how to calculate? You remember this one. Don't change anything. Just follow the equation that given to you. Okay. So you remember this is A minus A ration. The product is 2B plus C. Okay, the stoichiometry for the A is 1, B is 2, C is 1. So how to get the delta HRX at standard heat is C is 1 and B is 2. Okay, and then reactant minus 1. Okay, this is plus for the product, this is minus, so you can get like this, similar to this one. Okay, the C is product, so plus, this is plus 2, this is minus 1. Okay, you can get this one. And then you can get the delta HRX 400 though become like this the equation, and then you calculate. Okay, this one is from this, then you get this, and then 400 minus 2 T reference minus 298, and then you can get like this. Okay, not the inerts never enter into this calculation of delta HRX and also delta CP. Okay, inert not included. Okay, this is the data that you have to calculate when you want to solve any question for the X or for the T. Okay, here and here, just these two. Okay, and then this is algorithm to show to you for the CSTR algorithm. Okay, this one is how to find the T and V when the X is given. Okay, the solution, you have to calculate T for the linear progression of calculate T, and then you calculate when you get the T, you can calculate for the K. You can remember for the Arrhenius equation for the first slide, first or second, or first slide, third slide. Okay, for this chapter. When you get T, you can calculate the K, and then you can calculate for the KC also. This K, capital letter K, is for the reversible reaction. Okay, and then how to get this one? You have to calculate in the bracket of the red law, the red bracket in the red law. Okay, if you can remember, you can see you can get the K when you write for the red law. Okay, from the concentration, and then you put the X. For example, Ca equals Ca naught 1 minus x, something like that, okay? And CB, theta B minus x, all that one. Okay, and then you can get the red law. The red law lah ni, negative RA from the red law, then you can calculate the V, okay? Can you understand? And then two, you can also find the X and V when they give you T, okay? So one is they want you to calculate for the T, and then you get for the V, and also you can be asked for the X, and then calculate for the V. Okay, for the V, for this one, you calculate for the K first, and then KC. This is reversible reaction. Maybe all are reversible reaction. And then you can calculate X from the KC in the bracket, and then you can get the red law, and then you can calculate the V. Okay, and the third type, there is type one, type 1, type 2, and then type 3, the V given, but you have to calculate X and T. Okay, what the difference? This is find T and V, ini T and V tau, ini X and V. This one at the same time X and T, okay, when the given is T. When the given is B. So the solution, this is a famous one. I don't know whether this will be for the exam, final exam or not. But this is the famous one. You have to find the X and T at the same time by plotting the X energy balance and also X mole balance. So you have to plot this one, XEB, usually the straight line, and the X and B. This is from chapter 1 to chapter 4. You can get this one, and then at this one at here, at the point you can get the X and T at the same time. Kita panggil apa ni, titik pertemuan ni? What point this one? Okay, you can point apa kalau point
intersection ada.
intersection. Okay, the intersection is the answer for this type of question. Okay, so the X and T. Okay, I give you, I send you in the WhatsApp. There is for me, if I am a student, there is a flow chart that you can see your WhatsApp. In page 5 to 5 in the textbook, there is a flowchart for this type of question. Okay, you can see your phone, and then for example, they give you the elementary irreversible liquid phase reaction A to B. Okay, so all the FNO, CNO, KNO, E, CPA, delta HRX, CP product is 0 theta, I is 0. Okay, they all given, and then this is for the example for the CSTR. Okay, so the design equation for the CSTR is V equal Fn naught X over negative RA. Okay, see your handphone. And then red law, you can get negative RA. They give first order negative RA equal KCA. Then you can get also the Arrhenius equation. K equal AE epsilon minus ERT or K1 exponent E over R 1 over T1 minus 1 over T. Okay, and then stoichiometry, you know, this is liquid phase reaction, so you no need to consider about the 1 plus epsilon X. You just consider about the CA equal CA naught minus 1 minus X. Okay, and then you combine V for the box, second box. You combine V Fn naught X over the negative RA. You put the negative RA as K CA naught 1 minus X. And then you can be, the problem may be whether the left hand side or the right hand side. Okay, you see the right hand side is similar, is same with this in the slide type 3. Okay, type 3 question. Okay, where they want you to calculate for the X and T, okay, when the V is given, okay. So how to calculate this one? Two equation and two unknowns, okay. This is when you want to use the tau, okay. The tau, if you use the tau, is like this, X and B, X, apa, material balance, mass balance, equal tau K over 1 plus tau K, where the tau is V over V naught, V CA naught over FA naught lah. So the V for the MB become like that one. For XEB, this type of this here they consider about the UA, about the heat exchanger, but you will not calculate for the heat exchanger, so you can ignore the first term. You just consider for the last one, CPA T minus T naught, okay, over minus delta H Rx, okay. That is for the XEB. So you can get the XMB, and then you can get XEB, and then you can plot the plot X versus T like that one, and then you can get the X and T at the same time, okay. You can, for the X and B, you can use the tau, and you can also, if you don't want it, you can also get the MB without the tau, okay. There's many example, okay, from your seniors, from the past year's question that use that calculate the XMB without using the tau. You can get like that one, okay. It's not compulsory to use the tau, okay. That is for the type 3. And then for the left hand side, you can get the X. You can calculate the X and the V. The V and T, this is type 1. By the X is given. Okay, this is the simple one. You just follow the step. For this one, you need the K. You can see in the slide, you need the K for this question. K and small K. And then you can calculate the T. Okay, to get the K, you can calculate the T. Okay, T is you can ignore the UATA, and then all that one, you just get the T like the T in the slide, okay. And then you can calculate when you get the T, you can calculate the K, okay, from the Arrhenius equation. And then when you get the K, you can calculate the RA and also V, okay. RA, you know, negative RA equal KCA, so CA naught 1 minus X. CA naught is similar, PRT tu. Use the gas, general gas equation for the CA naught, okay, like before. Okay, can you understand? Can you get what you have to do in your chapter 8? What you have to know in your chapter 8? The type of question is like that one, So chapter 8 is quite long. You, I suggest you not to waste your time for chapter 8. Usually you have to spend more time, okay, for chapter 8, because chapter 8, one question from chapter 8 in your final, okay. So number 4, question number 4. Number 5 is for chapter 10, okay. So It's not difficult, but you have to be careful, okay, to answer for chapter 8. Okay, this is other example, adiabatic liquid phase in a CSTR. Okay, so given x is given, and then you have to find t and also v here. All this one is given. Okay. Okay, how to calculate that one? So you have to follow this step. Molecular equation, you cannot see this one. Molecular equation, because the CSTR, so V equal Fn of X over negative RA. Okay, so this is for the first order, so you can get this one. Stoichiometry, because of the liquid, so just Cn naught 1 minus X. If the gas, you have to consider 1 over 1 plus epsilon X. Okay, now you combine this one or all this one in here, so you can get the Fn naught and Fn naught. Fn naught is this one minus this one, you get X. This is the red law, Ca. Ca is Cn naught 1 minus X. So this one is for the tau. This is from the formula textbook, so they like to use tau, so they can get the V in term of tau like this. Tau is V over V naught kan, pergi bawah ni V naught, so tau. So you can get C naught cancel, and then you can get the 1 over K X over 1 minus X. And then the energy balance, this is the energy balance to get the T. And then because the equation just A to B ni. A to B je. So you can calculate the T when the X is given. Okay, T is equal this one. You can calculate the K from the Arrhenius, and then you can calculate the tau when you get the K. This one, get the K, and then you can calculate the V when you know the tau. Okay, this is example now. This is tadi tu adiabatic liquid phase. This is adiabatic liquid phase in a CSTR. Okay, adiabatic liquid phase in a CSTR for apa? Same, but this time you find X and V. This time you find T and V kan. This one is X and V. All is given, and then same you follow this one. This is the CSTR. Then you combine, you get the tau. Then this time you want to calculate the X and X and T. So this one you can get the K like this from Arrhenius, and then this tau same similar. Okay, just change the T and the X. Okay, this is when you sketch the XEB versus T. This one is the type 3. Okay, XEB. This one is the last one. To get the intersection tu. And then this is XEB energy balance. From the exothermic relation, delta X is negative. Okay, delta X is negative. Therefore, delta X is a positive number. This one. Okay lah, sebab dia ada bracket ni kan. They just want to show you the graph. Okay, the diabatic energy balance is satisfied along this line. This is for this one. This is for the negative one. Okay, Pada positif, pada negatif, jadi kata negative number. So you can get whether the X like this or the XEB, the XEB is like this or the XEB is like this, okay? Depend on this one, okay? Data HR ada. Kemudian you can get the X and B. You can calculate from by using the tau, you can get the X and B. And then the mobility is satisfied along this line, okay? So you can get like this. So you can answer this is X, this is the T that they want. Okay. If you are smart enough, okay, you can predict where the intersection is, and then maybe you no need to plot, because for this plot you need time to calculate all the data, and then you plot the graph, right? So if you are smart enough, no need to calculate for all the data here or here. This is for example, just calculate for here, okay, and then you can get the intersection. You can save your time, okay. So sometimes the T, this one the T. Sometimes they do not give you the range of the T. So you have to try and error or think about the range of the T. That's why maybe you no need to calculate all the T. Just calculate where the intersection is, and then you can get that one. Okay. But if you can use the Excel, in the test they allow you to use the Excel. I don't know in the exam. Okay. So if you can use the Excel, is better lah. Easy for you. Okay, this is example. Second order reaction in a CSTR. Okay, this is the example for question for chapter 8. Okay, the acid catalyzed irreversible liquid phase reaction. So this is liquid phase reaction. A to B is carried out adiabatically in a CSTR. The reaction is second order. This is for the red law in A, and then the feed which is equimolar in water which contain the catalyst and A. Okay, so A plus water enters the reactor at temperature 52 and total volumetric flow rate there adalah 10. The concentration of A entering the reactor is the 4 molar. So the question is, what is the reactor volume to achieve X equal 0.8, and what conversion can be achieved in V equal 1000 CSTR. And then what is the exit temperature? How to solve this question? So first one, you have to sketch the system, and then you can get you can see what they want. Okay, this is A plus water. You can see this is all given. Okay, 52 is, you have to convert to Kelvin, 325 Kelvin, and then other additional information they give you, this one. Why they give you? Because this is the chapter 8 that you have to calculate for this one. Okay, so how they calculate? Wait. The K is given at the 20 degrees Celsius, this one. But the 52 degrees Celsius, this 3 to 5, there is no K. So you have to calculate. Okay. So this is the part 1. What is the combined mole balance? Red law and stoichiometry that give the reactor volume as a function of temperature and combustion. So you have to arrange the equation. Okay, so V, this is more value for CSTR equal Fa naught X over negative RA. Because of second order, you can see in the question, the reaction is second order, so you can get negative RA equal K Ca power of 2. So this is because of the liquid catalyzed reaction, kan? Acid catalyzed kan? Acid catalyzed, so the liquid, so no need to consider about the 1 plus epsilon x, so just Ca equals Ca naught 1 minus x. Then you know this one, Fa naught equals Ca naught V naught, and tau also you know V over V naught. And then you can combine all to this one, and then you can get like this. Okay, and then you can also calculate for the tau equal this one. This is for the V, this is for the tau. And then what is the equation that gives x solely as a function of tau, k, and Ca naught? So they calculate lah. They calculate This is what This is how to calculate the x kan from this one. You know about this one? Yeah, negative b ab 4ab plus something. This one for x. And then they get the x equal this one. And then for they simplify the this one tau k Ca naught as a dA. dA is Damkula number. Sometimes they ask you what is Damkula number. Damkula number is the tau k Ca naught. Damkula, how to spell DAMKOH LER. The O is the O which has the apa tu tank point kat atas titik atas dia. Okay, Damkula. You can search in your textbook Damkula. Okay, so they can get the when you use this one, the Damkula, this one can be simplified like this. X be equal this one minus this one. This is the Damkula so it become like this. You can accept like this. Okay, so that is the X and B. The XEB, what is the equation that obtain that one obtains from the energy balance that gives X as a function of T. So energy balance, the equation is like this. So because you have the water, you have to consider the CPA for the PA and also for the water 50% of the day water. Okay, and then this equation become like this when you rearrange the T outside. You bring the T here, then you can get this one because you want the T. You want to the T in term of X. Okay, so you can get finally T equal 325 plus this one 90.1 X because the question asks you at the 80%. This one. So what is the volume conversion on exit temperature at X equal 0.8? Okay, so you can get the T first. T is at 0.x equals 0.8 is this one, T97.7. And then you get the T, you can put the T to get the K. This one is the K. To calculate for the K, small K. Kan? Betul ke? Betul lah. And then when you get the K, you can calculate for the volume of the CSTR. You can see if the question in sequence, they ask you first is volume, The second one is X and then the T. Kan? But in your solution, what is the first you can get? T, kan? You can get the T. And then you can calculate for the K. And then you can calculate for the V. So it's not compulsory. You have to follow the answer from the question. Okay? Because here you can get the T first. And then you calculate the K. And then you can get the V. When you get the K, you can calculate the V. So T, K, and then V. Can you understand what I mean? So it's not easy, that's why I said for chapter 8 you have to spend more time, okay? Alamak, mana ni? Okay, that is all for that question. This is sketch part B. When you want the X and T, this is so you have to sketch for both XEB and XMB. XEB, this one, can get this one, and then the XMB is like this, okay? But please search for your seniors past question which do not use the Damkula number. You can calculate without use tau. Okay, but it's up to you whether you want to use tau or without tau. Okay, to get the this plot. So the exit temperature and conversion you can get from this one. Write polymer program to obtain the exit there. Okay, you can also calculate by the polymer. We can generate XEB and XMB. The T curves by incrementing T and calculating the function. So the answer, please study the polymer. Okay. This is not included. This is reversible ration. Okay, reversible ration. Actually, in chapter 8, they always ask you using the reversible. But sometimes they use irreversible, but usually they ask you the reversible. So what is the difference? The difference is the K lah. You can get the capital letter K from the reversible. Okay. This is reversible, for example. So for the reversible, choose X. You calculate T, you can calculate T from this equation. Okay, this is equation, the general equation from the chapter 8 to get the T. And then you can calculate the K, small k. And then calculate T over T naught. This is the stoichiometry. If the gas reaction, if the gas reaction, you can use this one for the reversible reaction A to B. A2 to B, okay? Then you can calculate this one. This one is the difference, just this one, because the reversible reaction. Okay, what I said to you, you can calculate this one from this one, okay? Because at the equilibrium, this equal negative RA equal 0. So Kc equal Cb power of 2 over Ca. So if you put the Ca as in term of Ca naught and Cb also in term of Ca naught, so you can get the Kc because you can calculate the Ca naught, okay? And if you know about the X, you can calculate for the Kc, okay? Finish plot this one is reversible plot. You can see this one. This one is we can now use the technique developed in chapter 2. chapter 2 lah ni, CSTR. CSTR is the area of the segi empat tu kan. And then for the PFR is under the curve. This one. Ini panjang kali lebar. Okay. Then this is for the, this is from chapter 2 ni, shaded area. Okay. For the PFR under the curve. If 70 here is 40 here. But the axis must be F0 over negative RA. If no F0, you have to multiple with the F0. This both is F0. Why here? And this is for the CSTR. If 0.4 only here, because the touch the point that touch the curve. Okay. If 70 like here lah, 70 because the curve is here. This is for chapter 2. This is later staging. This is CSTR plus PFR. Okay. This is 40 for CSTR and then extended to 70 by PFR. Okay. This is the other way around. PFR and then this one is CSTR. Okay, 70. Have to go here because the curve is here. That's why. Okay, and then this is steady state PBR with exchange. No, we will not study here. This is okay. This is Y. You can remember what is Y? Y is P over P naught, right? The pressure drop. Okay. This is the pressure drop. This is, you will not study because the UA. Sketch TA versus V for a high and low coolant rate. Only also know. This is a coolant rate. TA. This is any other example. Exothermic reversible reaction. Okay. This one is reversible. Why is the maximum in the rate of reaction with respect to conversion, hence with respect to temperature and the volume for adiabatic reactor. A plus B reversible to 2C. Maximum rate of reaction K kan, respect to X. T and V. Okay. So this one is, the reaction is A plus B to 2C. So become like this. A plus B become 2C. Because reversible become like this. Then negative RA is like this. So can get like this one. Terkena. Betul lah. This is K. This is the all in bracket here. When you put the CA in CB, CC in term of CA0. Okay, you can get all this one. And then because of the gas reaction, maybe you have to consider about the epsilon. So you have to consider about the pressure drop and also temperature change. So you have to consider about the T0 and T, P over P naught also. So you can get this one. This is for the T. Okay. A term dominates. B term dominates. Curve A increase with T. Curve B decrease with T. Yalah. Atau tembang kan. Then this is other example for adiabatic PBR. This one is same reaction, adiabatic PBR. Okay, so all given what they want. They want to determine both the conversion and temperature for polymers. Then this is solution for more balance. This is when stoichiometry, when you consider about the apa nama dia, y is P over P naught pressure drop. This is the example how to get the T in term of X. This is very important. T in term of X or X in term of T. When X in term of T, you can get the plot. Okay, for the this is plot for the energy balance. Okay, this one T equal T in term of X. You can get really X in term of T to get the T. Okay, this is the apa nama dia polymer. I think that's all for. Okay, you see, what tadi? You see this one. This one. This when you combine. This is for the reversible reaction. The K is given, the Kc also given. Then you can calculate this is PBR. The mole balance for the PBR. See, this is for the MB, XMB. Okay, XMB for the equation like this. This is reversible. Okay, you have take the P and T into consideration also. Pressure and temperature. At equilibrium, this equals 0. So you just solve this equation to get the X in terms of Kc. Okay, if you can calculate the Kc, you can get the Xe. This is the X MB, more balance, right? More balance, right? If with T is EB, energy balance. That's all for the chapter 8. This is the calculation, the example. Get the CP. Okay, that's all for the chapter 8. Any question? You can see this is the example. This is example, the question for chapter 8. Okay, we have 2, 3 example. Okay, that's all for the chapter 8. Okay. Any question?
Doktor nak tanya.
Uh,
Since tengok kat example ni pun macam banyak yang guna polymer, so memang
tak.
dia wajib guna polymer ke?
Soalan in the exam, they will not ask you to use polymer. Don't worry.
Oh, okay.
Give me 5 minutes, okay? Rehat sekejap. Sorry. Any more question? Any more question? Tak ada eh?
So far, no question, Doctor.
No question. Okay, good luck for the chapter 8 eh. Chapter 8 is not easy. For me is quite long answer. Same like maybe similar like chapter 10. Okay. So you will do your question from Wednesday, and then if not finish, we will continue Sunday next week, and then maybe 1 hour also. 1 hour for the question, and then after later 1 hour is for the chapter 10, my lecture. The lecture for chapter 10 is quite simple, but the answer is not easy. Okay. And then I will, inshallah, I will mark your question one, test 1 and test 2, and will give you the carry mark before our exam. Your exam is on when? Your exam for the CRE 10 February ke? Betul tak?
Yes, Doctor.
10 February So 10 February 9 o'clock. So I have 1, 2, 3 weeks only. To mark your answer. Okay, if no question, you can leave now. Please search for the various type of question for chapter 8 Okay. Don't use the same one. Okay, welcome.